All right, so I'm going to throw some weird stuff at you today. So far we've talked about arithmetic and geometric, right? Anybody got any issues? Any questions about how to use them? Running any trouble?
Can you do again where you find like 3 of the means in between?
Okay, so for geometric and arithmetic means?
The geometric one, yeah.
Okay, so let's just say I gave you, and this one might be obvious, but if it's super obvious, know that I still want to see your work. So let's just say I said find 4, doesn't really matter how many, right?
Yeah.
Find 4 geometric means between, and I say 12 and, let's just say, and 37,500. So if I were to say find 4 geometric means, all I'm really asking you is to find what? The 4 spots in between there. Assuming that this sequence is a geometric sequence. So that's it. So what do you really need to find? What one thing is super important to find to navigate your way around a geometric sequence? The ratio, right? And the ratio, you can find it 2 ways. The first way is you can just pull out this formula, which you already know. And you can say, all right, if I want the ratio in between these 2, I could use that for that ending term, that for the beginning term. I don't know the ratio, right? But I do know what place that's in. Because if there are 4 in the middle, 5, 6, that's in the 6th spot. So I could say that this term is in the 6th place, so 6 minus 1 is 5. Right? And then I could solve, but if you watch the math, I'm not even going to put the 5 there, I'm going to leave a 6 minus 1. What you do to find the ratio is you divide by 12, right? And that gets rid of that. And then how do I get rid of a 5th power? I 5th rooted. So I would have 5th rooted this, and the 5th root really came from that 6 minus 1. And that gets rid of your root and leaves you with just the ratio, right? Well, I just memorized that equation. That equation right there says the ratio is always the n minus mth root, place minus place, of the term over term. And that's what I did, right? I took that term that was in the 6th place and that term that was in the 1st place. But I can do that anytime to find a ratio, and then I don't have to think through this. The only thing you have to be careful about is this. If I 5th root something, I don't get absolute value, do I? But what happens when you square root, or you 4th root, or you 6th root? You would have gotten absolute value. And what absolute value of r means that r ends up being what? Plus or minus. So had that been an even, if that's even right there, then what you have to do is remember a plus or minus. So that's what I would have done. I wouldn't have pulled out this formula. I would have just said the 5th root of whatever that is. And when I do that, I get a ratio is 5. And I don't need plus or minus here because it's odd. So once I get 5, I can just go times 5, times 5, times 5, times 5, times 5. Are you with me? Yes, no? Okay. Anybody else have anything you want to ask me about anything going on with geometric, arithmetic, you name it? Nobody? Okay. So today, here's what we're going to do. There's 2 things, and these are math team kind of questions that you get asked. They show up all the time. They're super easy to do once you know how to do them. what I'm going to show you, like, so if you wanted to memorize how to do these, you could just memorize it. But I want to show you the why. And because it took like about 24 years ago, I was playing with these. I'm like, how do you do these? And I sat with them for like 3 or 4 hours, and I figured out how to do it on my own. I was really pumped. And then like a year later, I got these textbooks, The Art of Problem Solving. And it had a whole big section on strange sums. And I was like, crap. So everything I come up with had already been written about. I thought I came up with something clever and unique. But anyway, they call them strange sums, so I continue to call them strange sums. But there's 2 kinds I'm going to talk about. The first one is when you're adding fractions. This is not a geometric, it's not an arithmetic, it's a different kind, but it is a converging sum. Now, what did we say about converging sums yesterday? Like when I was walking half the length of the room, and then the other half, and then another half, I was converging on what? On the one length of the room, or I was getting closer and closer to a certain number, right? And if I go forever, I'll hit it, but if I ever stop, I won't, right? But the key was, every time I added a new term, the new term I added was what? Or maybe a third or a fourth or whatever. But in that example, it was getting smaller. Everything I added was getting smaller and smaller and smaller and smaller. Now look at this. This first number is 1/18. The next number is 1/28. The next number is 1/40. I'm continuing to add a smaller and smaller number, aren't I? But the key is there's a pattern. And sometimes they don't have it broken up like this. Sometimes they just write 1/18, 1/28, 1/40. And it's your job to see or figure out that it might be patterned like this. But do you see the pattern? What would come? Do you see it? 3, 6, 4, 7, 5, 8. What's coming next? 6, 9, and then 7 times 10, whatever. So here's what I noticed years ago. And you might, in a million years, I would never want to do this, but it helps with solving this problem. So I'm going to show you the why, and then all you got to do is remember the hows. Everybody locked in? Okay? Because you might figure it out on your own, but it's going to be harder. So what I noticed was, anytime you have 1 over a product of 2 numbers, you could rewrite this expression, and again, why would you want to do this? Only in the context of this problem. You could rewrite it as a product of a fraction and a difference of 2 fractions. And the way you do it, like, it'll be easier to look at this. 1/3 times 5 is the same thing as not 1/3 minus 1/5, but 1/3 minus 1/5 times 1/5 minus 3. So literally, 1/3 times 5 is the same thing as 1/3 minus 1/5, 1/3 minus 1/5 times 1/5 minus 3, which is 2. And you can look at it, do the math on it. If you do the math on this, you end up getting, what, 5/15 minus 3/15, which is 2/15, and 2/15 times a 1/2 gives me a 1/15, and that clearly is a 1/15. Now, if you're looking at this, you're like, well, that's stupid. Why would anybody ever want to write 1/15 as this? This is why. Every one of these expressions, and this is not one of these, but every one of these expressions, I could rewrite using this process. And if I did it, look what would happen. So this first part ends up being 1/3 minus 1/6 times 1/6 minus 3. This one ends up being 1/4 minus 1/7 times 1/7 minus 4. But again, that's a 3. This ends up being 1/5 minus 1/8 times 1/8 minus 5, which is again is a 3. And if I keep doing this forever and ever, I get this long sustained pattern, which still is horrible looking. However, because every one of them has a 1/3, what am I allowed to do? Factor out the 1/3. And once I factor out the 1/3, these parentheses aren't doing anything anymore, are they? Are they? And if they're not, I can completely ignore them and start adding stuff together. But what I notice when I start adding this stuff together is, look what happens. This negative 1/6 eventually cancels with a positive 1/6. And this negative 1/7 eventually cancels with a positive 1/7. And this negative 1/8 eventually cancels with a positive 1/8. And this is going to continue to happen forever and ever. But what's great is this These two that I canceled right here are separated by a term. Sorry, I didn't cancel that. That one and that. These two are separated by a term. The second you end up canceling back-to-back terms, what that means is everything else is going to cancel. Like this next term would have been 1/9 minus 1/12. This next term would have been 1/10 minus 1/13. So from that point on, the second you get back-to-back cancels, you can say, everything else cancels forever and ever and ever and ever. And what do I have left? That times this plus this plus this. And that I can add together and simplify. Are y'all seeing that? Now, do you have to know this whole process? No. What I would probably do if I had this problem is I would skip straight to this step. I would just say, all right, the difference in all of these is 3, right? So I just put a 1/3 out front. And then I write 1/3 minus a 1/6, 1/4 minus a 7, 1/5 minus an 8. And I just write out enough. Usually I write 3 or 4 or 5, but sometimes I don't even need that many, but just enough so that I can start canceling. And as I'm canceling, the second I hit back-to-back cancels, I know that everything else is going to be canceling if these are infinite, forever and ever. I just would have to keep writing them, but they were going to continue to cancel, and then I just gather up what's left, find a common denominator, which is kind of annoying, but I try to make the problems at least tolerable, and then add your stuff up and multiply. Are y'all seeing that? All right, let's give it a shot. What about number 1? So help me out. With what I just showed you, assuming you were with me and not like staring off at a wall, some of y'all struggling with ADD issues. Right here, what's the first step if you wanted to skip the whole process and just jump to the actual?
Find the difference.
So the difference in all of these is 2. So I'm going to put a 1/2 out front. And then I'm going to rewrite each of these as what?
1/3
Third minus a 5th. A third minus a 5th. And then a 5th minus a 7th. And then 7th minus a 9th, right? Forever and ever. And then I'm going to look at this and start canceling. Now the great part about this one is immediately I get back-to-back cancels. And the second that happens, well look, everything else is going to be canceling as long as it's infinite. So all I end up with is 1/2 times that 1/3. So something like that ended up being pretty simple.
But aren't these just like infinite series
But they're not arithmetic and they're not geometric.
with the?
They're just
What isn't it?
strange.
Technically geometric with like a.
It is not. Because geometric means, the definition of geometric means that if I take this fraction and put it over this fraction, I should get the same thing as that fraction over that fraction. They would have to have a common ratio. And you're not multiplying by, like, think about it. If you look at these numbers, there is nothing I'm multiplying that by to get to this. That's the same as me multiplying there to get to this. It's just different. So it's not geometric. And sometimes you'll be given this. And what would I do if I was given this and it wasn't really obvious that it was this pattern? I'd probably go down my list. Is it arithmetic? No. I mean, you can check the common difference, but there's no way that that minus that's the same as that minus that. Right? I mean, I think we can all probably agree with that without actually checking and finding common denominators. Is it geometric? Well, maybe you don't know. So I'm going to put that over this. If I put that over this and multiply by the reciprocal, I get 15/35, which is what? 3/7. But if I put that over this and multiply by the reciprocal, I get 35/63, which is 5/9. Well, those aren't the same, so it's not geometric. So at that point I go, well, what am I going to do if it's not arithmetic, not geometric? Well, maybe it's a strange sum. And by the end of our whole lesson, you're going to have like 5 or 6 different things you're going to be looking for. Most of them arithmetic, geometric, but there's going to be a couple of these other ones we're going to talk about today, tomorrow, Monday, Tuesday. Y'all with me? Okay, so let's look at a different one. What's going on here on part B? It's kind of a lot, right? They're trying to intimidate you, get you to assume the position. We don't assume the position, right? We look at it, and the very minimum I can look at it, is this arithmetic? No way, because arithmetic would look like a what? A line, and that, then anybody go, well, those are lines. Well, lines in the denominator are not lines. So there's no way this is arithmetic. Is it geometric?
No.
Well, geometrics, they have that geometric formula look, right? Like T1 times R to the n power. I don't see like 4 times 5 to the nth power. I don't see anything near that. But if you still don't notice that, you could always write out a couple terms, couldn't you? Right? Now this one goes through the fifth. But I want to show you what we've done so far is only look at infinite ones. Sometimes they're finite, but let's just write out these 5. I tell you what, let's do this. Change that 5 to a 15. Just change it to a 15. Now I'm going to write these out, but I'm going to do yourself the favor of not simplifying anything. So check it out. First, I plug a 1 in. What do I get when I plug a 1 in?
15.
No, don't simplify anything. What do I get when I plug a 1 in? 1 over 3 times 5. All right, plug a 2 in, what do I get? 1 over 5 times 7. Plug a 3 in, what do I get? 1 over 7 times 9. Right? And I'm going to keep doing that all the way until I plug a 15 in, which gives me a 1 over what?
1 over 31.
31.
Times 33.
31 times 33. Well, at the very minimum, I look at this now and I go, oh, that's one of these strange sums, right? The only difference is it doesn't go forever. And if it doesn't go forever, I can't cancel everything out. So I'm going to let you see what's really happening here. And I'm going to write them all out so you can see it. So, every one. And then I'm hoping you're going to learn from this a little trick to save you from having to write them all out in the future. So let's check this out. Right here, what would go out front?
1 over 3, or 1.
1 over 2.
Yeah,
Because
1
5
over-
minus 3, 7 minus 5 is 2.
Parentheses, 1 over,
And then?
1 over 3 minus 1 over 5.
Now I'm going to write every one out. That's plugging a 1 in. This is plugging a 2 in. Now this is going to be really annoying to watch this. In fact, I may not. Let's just set it right here. I tell you, I really want to go this far. Here, how about change that 15 to a 10. So at a 10, this would be 21 and 23. Sorry, I just trying to illustrate a point. There's no point in making me realize it. So, so 1/15 minus 1/17, 1/17 minus 1/19, 1/19 minus 1/21, 1/21 minus 1/23. So this one's not infinite, it's finite. And what would happen when you go to cancel now? Obviously those cancel, but we don't just cancel everything because look, at the very end of the day, not everything cancels. Now here's the beautiful part. You remember the first problem we did? We had, in my example, I had 3 problems that didn't, or 3 fractions that didn't cancel. On a problem that's finite, if there are 3 things that don't cancel on the front that are positive, there's going to be 3 at the end that don't cancel that are negative. On this one, there was only 1 term in the front that didn't cancel, that's positive. So, the very last negative one is not going to cancel. So in the future, when you're doing, does that make sense? Now I'll show you that pattern maybe one more time and then I'm going to just skip to that rule. So when I'm doing these, I normally, once I establish the pattern and I see what cancels, I don't even write it out to the end. I don't bother. I might write the very last term out, or maybe I'll write this out and I'll say, okay, if I only have 1 term left here, then I go and grab the very last negative. And that's all I have to deal with. I don't know why I wrote it so far apart. And then hopefully, and by the way, do y'all know how to do fractions quickly?
You multiply the bottom 2 for the denominator, and then for the top one, you subtract the first denominator from the second denominator.
I mean, like, y'all know this little trick. Rather than find a least common denominator, you can just real quickly go that times that minus that times that over that times that. It's just a quick way. So 23 minus 3 is 20 over 69, and then just multiply that 1/2 in. Just kind of a quick way. You can sometimes do it in your head. Like I could look at this and go 23 minus 3 is 20 over 69 times 1/2, 10 over 69. It just enables you to get there a little more quickly, I think, but anyway. So let me show you something else. Okay, check out number 4. So number 4, it's finite, doesn't go forever. So let's see if we can figure out the pattern. What goes out in front? 2. Every one of these is a difference is 2, so 1/2 out front. And then I'm going to write 1 over 1 minus 1 over 3. 1 over 2 minus 1 over 4. 1 over 3 minus 1 over 5. Now again, I'm not going to write all of them out because I just don't feel like it. And sometimes it goes a long way. So I'm going to think about my process. So I'm just going to put plus dot 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 plus 1/9 minus 1/11. Now let's see if it works, what I've been saying. What cancels do you initially see?
The 3 and the 3.
Okay, what would have been the next term here? 1/4 minus 1/6. So the 1/4 would have also canceled. Y'all seeing that? And the second I cancel the 1/4, what do you see?
The 1 and the 2 left over.
Back to back cancels. And what does that mean? If it was infinite, it would mean what? Everything else cancels. But because it's finite, what it means is all the junk in this middle is going to cancel, but it did leave 2 positive terms out front. So, if 2 positive terms out front are left, what should be left at the end? 2 negative terms. Not the last 2, because this was like first and third. So it'll be last and third from last. But it's the last 2 negatives. So I grabbed that last negative, which was pretty obvious, right? Negative 1/11. What is the one that would have been right before that? Now think about it. You're going 1, 3, 2, 4, 3, 5. So 9, 11, what would have come before that? 8, 10. So you would have had 1/8 minus 1/10. Are you seeing that? Yes, no? So grab the negative 1/10 and the negative 1/11. I'll even show you something better than that. If you have these 2 and these increase by 1, then take your last one, decrease the denominator by 1. If these first 2 increase by 3, like if it goes 1, 4, then you'd go 11, 7. So there's patterns all over the place, but these first 2 negatives, last 2 negatives, and it keeps you from writing every single term out and really seeing what's going on. But I got to tell you, if you did write out every single term, it'll probably stick in your head a little bit better, probably a little less to memorize. All right, what about, think something else. How about, look at number 8. This again is finite. So if it was infinite, that one we just did was infinite, it'd be really easy. All you'd have is the 1/2 and the 1 and the 1/2, and you'd be finished. Because everything else would cancel. All right, so check out number 8. See if we can do it without writing everything. Because that's going to be a lot of writing to get all the way to there. So here we go. So what would go out front? 1/4, because the difference between each of these is 4. And then if I started writing 1/2 minus 1/6, positive 1/4 minus 1/8, positive 1/6 minus 1/10, I'd write out a few more. Since I'm going 2, 4, 6, what's the next one? 1/8 minus what? 1/12, and then plus dot dot dot, and I know it's going to end. It's going to end with 1/20th minus 1/24th. But let's see if I can do the math without writing all this out. So start canceling. Those 2 cancel. They're not back to back. Then what? The 8s. Now once I hit those 8s, what do you see? And once I hit back to back, that means all this other middle stuff's going to cancel. But I know it's not going forever, So how many were left in the front? 1/2 and 1/4. And then this 1/4 that right here. So at the end, I know I've got a negative 1/24, but since that went up by 2 in the bottom, what am I going to do here?
Down by 2.
So that gives me a negative 1/22. And I didn't have to write it all out. And hopefully I could knock something like this out in 30 seconds if I ever went through a ciphering, if I was a cipher and be able to get these. Because they're pretty doable if you have a game plan. No, worst comes to worst, write them all out. If you write them all out, you'll see it. Now, finding a common denominator here would not be super pleasant. So how do we find common denominators when it's not obvious?
Cross them,
What did we do? We learned a process to find a least common multiple.
Oh, prime factor.
Did the prime factorization, right? So this has got a 2 and a 4. Well, that's got a 4. So really it boils down to these two. This has got a 2 and an 11. This has got a 2 cubed and a 3. So what am I going to need in my factor? A 2 cubed, a 3, and an 11. So I'm going to need an 8, a 3, and an 11. And 24 times 11 is 264. Right? So my common denominator is 264. And again, I try to keep these numbers a little bit better on a test. You would have to say, you'd have to go, all right, I got a common denominator of 264. If you were doing this, 2 goes into 264, 132. 4 goes into 64, 66. 22 goes into that, 12. 24 goes into that, 11. And then you would just add all that up, subtract, add and subtract over 264, and then cancel whatever you could possibly cancel. And again, most of the time the math on the test would not be this ugly. Y'all with me? That's strange sums. And remember, the harder ones, I guess, are the ones where they go finitely and they have an ending. But you can deal with that ending pretty easily if you have a game plan. If it's infinite, like if this is not there, well then everything cancels. It doesn't end. And all you got to do is end up adding this, which is going to be significantly easier, right? So hopefully you'll see those. That is the first of 2 what I call strange sums. And I would encourage you to go back and do some other ones. Now I snuck a few other problems in here just to mess with you. Like for instance, number 6. Now, a lot of people look at a problem like this and they think, oh yeah, that's probably a strange sum. And they start playing around with, oh, 4 times 5, maybe, I don't know, maybe 2 times 5, 3 times 5. And they get a little confused here. Hopefully also you'll notice that 3 doesn't really seem to fit with it, right? Although you could have changed this to 3/30ths, 3/45ths. It's okay to have the same number in the top on a strange sum. You could factor that out also. Right? If you wanted to. But this doesn't really fit. But remember, just because it's ugly looking doesn't mean it's not arithmetic or geometric. Check the ratio. How would you check the ratio here? 1/10 over 3/20. So to divide by 3/20, you multiply by 20/3. Right? So my ratio is 2/3. Let's check the next one, make sure. 1/15 over 1/10. To divide by 1/10, I multiply by 10 over 1. Oh, also 2/3. So this ends up being just geometric. So don't look at something and be freaked out or assume it's weird. Go through your checklist that hopefully you'll have by the end. Is it arithmetic? Is it geometric? How do you know it's not arithmetic? I mean, other than the fact that you just found that there was a common ratio. How do you know? What does it have to have if it's arithmetic? Common difference? Now, you off the top of your head, you might not be able to tell, but is 1/10 minus 3/20 the same as 1/15 minus 1/10? 20 minus 30, is that the same thing as 10 minus 15? No, they're just not the same. So it's not arithmetic. But check those things. Don't forget to check them, even if they're a little bit ugly. Every year I put problems on there and I see people trying to do weird things, but all they really have to do is check is to see if it's arithmetic or geometric and go from there. Hey, give me a reason why I'm not even going to bother to check to see if it's arithmetic. It's infinite. I can't add infinite sums anyway that are arithmetic. Can I? No. All right, what about this thing? I get people every year on these, and so does math tournaments get you tons of the time. It's just such a common little problem. Now, I see people all the time, they go, all right, it's probably a strange sum. It really looks like a strange sum, but but it's not broken up like this yet. So I see people go, all right, maybe that's a 2 times 5, 3 times 5, 4 times 5, 5 times 6, 5 times 8, 6 times 10, and then people just get confused because there's no pattern there, is there? Anybody see it?
Yeah, it goes like up by 5, up by 5, up by 10, up by 10, and up by 20, up by 20.
The next term won't do that, but you're right. And even if that was the pattern, do you have a plan for adding them?
No.
But that's good to notice that. You'll see it. What if I pulled out the 1/15th and the 1/30th and the 1/60th? What do I have now? I got 2 geometrics. I have this geometric where I'm multiplying by a 1/2, 1/2, 1/2, and I have this geometric where I'm multiplying by a 1/2, 1/2, and they're both infinite. Can I add up infinite geometrics?
Yes.
If the ratio is what?
Less than 1.
Between -1 and 1, is it? Okay, so how do I add the first part?
1.
First term over 1 minus the ratio. How do I add the second part?
Same thing.
First term, which is in this case is technically the second one, but it's the first one in that sequence, right? Over 1 minus the ratio. And then I just clean this up, right? That ends up being a 1/2, so this whole thing ends up being a 1/5. That ends up being a 2/15. And when I do the math on this, I get 3/15 plus 2/15 is 5/15, which is a third when all is said and done. Is that right?
Yes.
Or you could do this, remember our little trick? 15 plus 30 over 75. Is that right? This is 15, oh, I'm sorry, 15 plus 10. And I get 25 over 75, which is 1/3. Whatever. Y'all seen that? So far you have 4 things to check for on every problem on your test unless it's totally obvious. Sometimes it'll be obvious. You'll look at it and go, oh, the ratio's 2. Oh, common difference is 10. But if it's not, check arithmetic, check geometric, check 2 geometrics woven together, and check our first strange sum. So that's 4 things on the list that nobody seems to be writing down, but 4 things on your list that you should be looking for on every problem on your test that's not obvious. All right, here's the 5th. And this one is going to really require some clever manipulation. And, but again, so tell me what you see, and you can ignore the S right now. Tell me what you see on this set of fractions that are being added together. That's true, but they don't have to be.
Top is arithmetic, bottom.
The top is arithmetic, and the bottom is geometric. Now, it also happens to be a power of 3, you're right, but it didn't have to be. It could have been 2, 6, 18, 54. But the key is it's geometric on the bottom, arithmetic on the top. And if it's geometric on the bottom, doesn't that mean that the bottom numbers are going to be getting really, really big? Probably a lot more quickly than the top numbers? I mean, look at this. 4, 7, 10, 13, 16. 19, 22, here, 3, 9, 27, 81, 243, 729. Those are getting huge. So what happens if the denominators are growing more quickly than the numerators? What's happening to those fractions? They're getting smaller. And if you're adding smaller and smaller fractions, what's happening to the sum? It's converging. So I can't add this. All right? Now, that doesn't mean you can add every convergent sum with what you're going to learn in high school, but you got a fighting chance, right? So here's some really clever math. It's going to make no sense in the short run, but hopefully you're going to get to a point you're going to go, oh my gosh, look what just happened. So check something out. If this is what I'm trying to sum together, I'm going to name it equals S so that it's an equation. And an equation now, kind of like we did in our proof of the sum, remember the proof I did for the sum? I went through and I multiplied through by negative r. Do you remember that? And then added the two together? Well, I'm going to do the same thing here, except I got to be a little bit more creative in that negative r, it's not geometric. So what I'm going to do is I'm going to go pretend for a second, just pretend that there were just ones on the top. Then the ratio would be what? 1 over 3, 1/3. So I'm going to multiply everything up here on the top. I'm not going to put ones, but I think that way. I'm going to multiply both sides by negative 1 over r. Now in this case, the bottom part was times 3. So I'm going to multiply everything by negative 1/3. Now what do I get on the left when I multiply s by negative 1/3? And by the way, do this. So like you're going to have this written down, and I'm going to multiply this by negative 1/3, and I get negative 1/3 s. What do you get when you multiply 4/3 by negative 1/3? Here we go. 4/3 by negative 1/3, you get what? Negative 4/9. But instead of writing negative 4/9 there, like I did before my other proof, I'm going to slide it over so these denominators match. So that times negative 1/3. What happens when I multiply 7/9? 7/9 by a negative 1/3. Negative 1/3. What do I get? Negative 7 over 27. And I'm going to write that right there. What happens when I multiply that by a negative 1/3? Negative 10 over 81. I'm going to write that there. And if I keep doing that, all of these terms now line up. Now they're not going to cancel like they did before, but here's what's beautiful. 1s minus 1/3 of s is a what? 2/3 of s. That I can do. 4/3 and nothing is 4/3. Now here's what the magic happens. What's 7/9 minus 4/9? 3/9. 10/27 minus 7/27? 3/27. 1381 minus 1081? 381. What do you now have? Same numerator. And if I have the same numerator, as opposed to arithmetic numerators, what does this form? An infinite geometric sequence. Now, that doesn't mean my answer is this. This is just part of this equation now. But I can find the sum of that. So I'm going to bring down the 2/3 s. I'm going to bring down the 4/3. I'm going to take that new first term, the first term in this part. Is that making sense? I'm going to do a couple of these. I'm going to copy that down in my formula. My ratio of this is positive 1/3 now. 1 minus the ratio. And all I got to do is simplify this fraction, which is 1/3 divided by, that gives me a 2/3. And then to divide by 2/3, I multiply by a 3/2, which cancel those 3's out. So I have 4/3 plus a half, which is 11/6. And then the last step is to get rid of that 2/3 that I've been dragging around with the s. So multiply both sides by 3/2. And a little bit cancels, and I get 11/4. That's the 5th thing on your list. Let's do a couple of these, because these can be, there's a lot of processes, a lot of steps. And the better you show your work, guys, the less you're going to make mistakes. I have people just trying to get to an answer all the time, instead of showing some work, and they get lost, they forget to multiply by 3/2 at the end, all kinds of little stuff happens. All right, so help me out. What's the first thing I need to do on a problem like this? You just did it. I'm in coma today. What's going on?
It was the 1/3 that was on the other.
Name it. name it. I'm gonna call it S. I gotta make an equation of it so that I can actually do some algebra with it. Because if I don't make an equation and I go and multiply by something, that'd be like going to the bank, right? I can't just randomly go around multiplying by stuff. So I'm gonna make it an equation by saying, hey, all of this adds up together to give me some value of S that I don't know. Now, what is your kind of your pseudo ratio here? What's going on? Looks like you're that's what I'm gonna multiply by, -1/2. But I'm multiplying by 2 on the bottom, right? So on this thing, I'm gonna use negative, if it's 2 on the bottom, I'm just gonna put a 1 and negate it. That's what I'm multiplying both sides by. So -1/2 times S, -1/2 S. What's -1/2 times a 3/4? And where do I put that? Slide it over so that the denominators match. What's 5/8 times a -1/2? -5/16. I write that down. What's 7/16 times a -1/2? -7/32. And you can keep doing this because they both go forever. When I subtract, 1s minus a 1/2s is a 1/2s. 3/4 and nothing is 3/4. And then here's where the magic should start happening. 5/8 minus 3/8 is 2/8. 7/16 minus 5/16 is 2/16. 9/32 minus 7/32 is 2/32. And if this continues, which it does, what does that form? An infinite geometric sum. So how do I do this? I'm going to copy the 1/2 S over, copy the equals, copy the 3/4, and then I'm going to use my infinite geometric sum formula to add this part up. So how do I do that? I take that first term, which is a 4th, and I divide it by what?
1 minus 1.
It looks like the ratio is 1/2. So I go divided by 1 minus 1/2. And what is 1 minus a 1/2? And to divide by a 1/2, I multiply by a 2. And what's 2 times 1/4?
1/2.
1/2 again. What's 1/2 plus 3/4? 5/4. And if 1/2 S equals 5/4, I would just multiply both sides by 2. And I'd get S equals 5/2. Y'all seeing that? Now guys, listen. There was this old commercial for the Army. Now, my dad was in the military, I respect the military, but they had this commercial, they had 2 that were going at the time, and one was like, we do more before 5 a.m. than you'll do all day. I thought that was pretty cool, whatever. The second one they had is, we never take the easy way out. And I was like, no. Big giant wall, barbed wire at the top, door at the bottom. I'm going through the door. I'm not going over the top. So my mentality is always, I'm going to try to find the most, I want to show you why, but then I'm going to show you the most efficient way possible to get something done. Because that's kind of how I thought. And every now and then, I'm not going to say it's super rare, but every now and then somebody will say, man, I got an even better way. And sometimes your way is quicker, and I don't tell you because I want you to come up with it on your own if you're going to use it, as opposed to me just telling you how to do it. But most of the time, I'm kind of telling you the best way to go about doing something. So if you're going to take a shortcut, maybe make sure your shortcuts are working for you by checking. Because so many times I see people take shortcuts, and they're just not working. Or they're forgetting stuff. The best way to ensure that you're getting these right is to show this. I see people all the time that go, oh yeah, forget that stuff on the left. And they just get to here, and then they because they're not writing equations, they forget to multiply by 2 at the end or whatever. But take your time and write out these processes. It's not, you're going to find an AP Cal, it is not about getting answers. You'll do a 6-point, sometimes even a 9-point problem on an AP test. You get 1 point for the answer. It's 8 points for your setup. Literally. So just getting an answer might work great in Algebra 1, Algebra 2 a lot of the time, although not necessarily in my class, but you really need to focus on proving to the person grading it that you understand the process. And that's especially true on this kind of stuff that can be confusing. All right, let's do another one. What about this right here? And I don't even know if it's a strange sum. You tell me. It might be geometric for all I know. What do you see going on here?
This
So clearly right now it doesn't look like anything, does it? I mean, to a couple of you maybe it does.
Oh, I see it.
If you're able to see it. But if it doesn't, if you're not able to see it, go through the process. Is it arithmetic? Is 1 minus 1.5 the same thing as 5/8 minus 1? No, not arithmetic. All right, I've checked that off the list. Is 1 over 3/2, which is 2/3, the same thing as 5/8 over 1? No, it's not geometric. Is it two geometrics woven together? First of all, if it's not geometric, it's not going to be two geometrics. Now, it is true that every geometric sequence can be split up into two geometrics. That's actually a true statement. The ratio would get bigger on each one, but you could do that. But sometimes two geometrics are woven together where it's nothing, it's just weird. But this right here, just looking at it, that to that to that, and this to this to this, definitely not two geometrics. Is it a strange sum from the first kind of strange sum? No, because the numerators would all have to be the same, and they're not. So really, you only got one other option. So if you're going through this checklist and you have that checklist in your head, and you're like, well, for this to work, the top would have to be arithmetic. This would have to be, if that's a 3 and a 5, this would have to be a what?
4.
A 4. And I can rewrite 1 as 4 over 4. And if that's a 5 and a 7, this would have to be a 6. And I could change that to a 6/16. And now look at the bottom. Times 2, times 2, times 2, times 2. So it turns out this was one of those arithmetics over geometrics that are infinite. So I can add them. So I name it S. And what would be the first thing I do? This is you on your test. First step. Is it 1/2? Negative 1/2.
Yeah.
And I know it's negative 1/2 because I'm multiplying the bottom by a 2. So I do 1 over 2, but I negate it. So I'm going to multiply both sides by a negative 1/2. What happens when I multiply S by a negative 1/2? Negative 1/2 S. What happens when I multiply 3/2? I get negative 3/4. 4/4. Negative 4/8. 5/8. Negative 5/16. Negative 6/32. Yada, 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 right? But I'm literally doing the math there. Then what? I'm adding these. I'm using literally the Gaussian elimination process, which is the elimination process. That, except nothing gets eliminated this time. But 1s and negative 1/2 s, positive 1/2 s. 3/2 and nothing. And then here the magic happens. What's 4/4 minus 3/4?
1/4.
What's 5/8 minus 4/8? 6/16 minus 5/16.
1/16.
And this just keeps happening, doesn't it? Now, right now, I know that there are people in here going, wait a minute, I've noticed some patterns. Listen, I'm not saying these patterns are bad, and I know they're out there. I'm not going to teach you just how to memorize everything. I want you to understand processes, but make sure it's working for you. I think people in here, even after me showing you easier ways to do it, are always still looking for easier ways. Sometimes it's better just to accept the math, and if it really sticks out and it's really working for you, great. But so what's going to end up adding together here? All that. So here we go. 1/2 S equals 3/2. What's the formula for infinite geometric? First term over 1 minus the ratio, which is a 1/2. And 1/4 divided by 1/2 ends up also being 1/2 again. 1/2 plus 3/2 is 2. And if 1/2 equals S, S equals 4. Y'all with me? Hey, if you look at your homework tonight, there are finishing up these problems that we haven't finished. All right? And then it has this infinite sums practice. I don't expect, guys, I don't expect you to do all of these. What I expect you to do on this infinite, these are all math team questions. I expect you to come in here tomorrow with good questions. Tomorrow is essentially a big review day, a midweek review day. So come in here with good questions tomorrow from any of this stuff. Y'all are good.